button. And you need to control the volume here. The mic is kind of like 35.
No, that's good.
We're basically right now.
Okay, good, right? Good. Morning, everyone. So today we start with J.C. Gumberg from the Georgia Tech University. And not university, Georgia Tech.
Georgia Institute of Technology. Yeah, I mean, it's
Full name then.
yeah.
Please.
Okay. All right. Good morning. So we're now halfway through. So everybody's on their way to becoming experts, right? So no, right. Of course, it takes much longer, but hopefully you're getting some sense of these things. So today we're going to talk about something that may seem a little esoteric at first, but it's really critical. The force fields that are underlying all the simulations that we're actually doing. And in particular, I'm going to make reference to a tool that we developed now over 10 years ago in VMD called ffTK, or Force Field Toolkit, which is for making new force field parameters. And we'll see why that's necessary. And of course, feel free to interrupt with questions anytime. Better that you ask than hold it off and not understand something. Okay, so the force field, right? What is this? So this is the potential function that governs all the interactions between the atoms in our simulation system. Okay, so potential, if you remember from physics, you often write with the letter U. So that's potential energy. And we break it up into a few terms. So one we call, or the potential related to bonds, one for angles, one for dihedrals, and then a couple of non-bonded terms for van der Waals and electrostatics, or Coulombic. So looking at what the functional form looks like here underneath, there's my mouse pointer. You can see the bonds take the form of a harmonic potential. So that's, it has the distance squared times some force constant. And we sum over all the bonds in our system. Then we have angle terms. So bonds are two bodies. So that's two atoms interacting. Angles are three. So that's three atoms in a line that interact. And so that's the bending between those three atoms. Again, it takes the form of a harmonic. Then we have this different type of term called a dihedral or torsion potential. So that's four atoms in a line, and that is an angle. So the way you think about the dihedral angle, which is this phi here, is the angle between the two, the planes formed by the first three atoms and the last three atoms. So the middle two overlap. Another way I like to think about it, if I do this with my hands, the two atoms on the ends are my fingers, and then my thumbs are forming the two in the middle. And you can think about it as a rotation about the bond between those middle two atoms. Okay, so why it's different, so you notice it has this functional form of a cosine instead of a harmonic like the previous two, is because it allows for periodicity. So the rotation can go all the way 360 degrees around and come back to where it starts. So those are we'll talk about another term later, but these are the three main bonded terms. And then we have our non-bonded terms, which include what we call Leonard-Jones potential, or that includes, traditionally has this form 612. This term here, the 6, so you notice it's 1 over r. And there's a minus sign in front of it. So that means that's an attractive potential. That is induced dipole. So even neutral atoms can polarize somewhat. The electrons move away from the protons, and then they can attract each other electrostatically. So but it's pretty weak. That's why it's 1 over r to the 6. Okay? And then this 1 over r to the 12, it's a plus sign in front of it, or it's positive. So that is a repulsion term. So if the atoms get way too close together, they can't overlap one another, and so they should repel. And in fact, they repel quite strongly at close distances. Okay, that's why the 12 is there. So that's Leonard-Jones. And then the last term is, you might remember from your introductory physics courses, that is Coulomb electrostatics. So that's, Q1, Q2 divided by R. You might remember Coulomb force is 1 over R squared. So this is potential. So it's 1 over R. And there, of course, should be a force constant, sorry, not force constant, a Coulomb constant in front. You might remember K, 9 times 10 to the 9, or 1 over 4 pi epsilon naught. We're just currently writing this in units such that we don't put the constant there, but it is there. It's just hidden. Okay, so this potential function governs basically, with a few exceptions, all the interactions within our simulation system. Okay. But you can see there's a lot going on here. So the functional form, okay, not too difficult. Squares, cosines, okay, we know how to handle that. But there's a lot of different terms here that we have to provide to the simulation for it to be able to run. All these force constants, all these Ks, K bond, K angle, and that's for every single bond, every angle, every dihedral in our system. We need to have a different constant for those. In the dihedral term, not just the constant, there's also an offset, there's a multiplicity that we have to account for in the Leonard-Jones. There are these epsilons and sigmas, and then even the charges. You think, well, okay, I can look on the periodic table. I know what charge is on an atom or on a proton or on the nucleus, but the charges are actually partial charges. So we have to decide how to split the charge in our system up between different atoms, and it's not necessarily the way you would think. Okay, so we have to have ways to determine all of these numbers. Now, fortunately, if you're running a simulation just of a protein and water, or for that matter, membranes or nucleic acids, somebody already did all that work for you. So we traditionally use something called the charm force field, or more precisely, we use one called charm 36 or 36M. And that comes from the group of Alex McCarroll and collaborators. So in that case, for common molecules, they determine all these parameters, and you have these big files full of numbers like this that you can reference. But as we'll see, if we want to do anything outside of those common molecules, we are going to have to come up with all of those numbers for our specific molecules of interest. Okay, but before we dig into that, let me do a little bit of a digression to some. So I'm very pragmatic. So I want to spend some time talking about the file structure. It seems very boring, but you kind of need to understand what these files look like to then understand how to modify and make new ones. Okay, so let's start with the PDB file. Okay. So by now you all know PDB. You've all looked at 1UBQ, right? .pdb in your introductory tutorials. So many of you may know this already, but again, to make sure we're on the same page, let me just go through it carefully. Okay. So we typically start our simulations with a structure that comes from the Protein Data Bank, or PDB. This is, for some reason, it's not pdb.org, it's rcsb.org. So you have to remember that. Although nowadays, right, you might start with, if it doesn't exist in the PDB, you might start with one from AlphaFold, a predicted structure. Okay, and that's perfectly fine. And it will come in the form of a PDB file typically. So these contain, first of all, at the beginning of the PDB, there's a lot of information for you. There are a bunch of records that tell you, okay, like what species did this come from? What method was used to determine the structure? Are there missing residues? Are there missing atoms? Are there disulfide bonds? And a number of other important and relevant information are stored in those records. So I always encourage people, when you start with a new system, look at the header of that PDB file. There may be key information that you don't want to miss. Okay. Now, well, And then I say we only care, well, in terms of VMD, we only care about the atom records. So that's where you have all your coordinates, the names of the atoms, the residue names, and so on. Okay. One thing you probably already realized by now, that PDB does not include hydrogen atoms, right? Typically speaking, that's because crystallography can't resolve them. Their electron density is too weak typically, and so they don't see them in the experiment. Fortunately, we know there are tools that can add them very easily, like ffGen, which you already should have used by now. Okay. So looking at the PDB specifically, so it's an ASCII file, so it's human readable, and it's fixed width. Okay. So what that means is you can see I have a little counter down here. So every column is assigned for a specific purpose. So it's not like, so the spacing is important, in other words. This is one reason that we typically would recommend you don't modify these by hand, because if you change the spacing, some tools will not be able to read them. Okay. So better to use VMD, ffGen, et cetera, to modify these files, which will respect the spacing. Okay. So you have some like atom. Now there are some others, but we're focusing on the most common one, atom here. You have the next one is index. Then you have name, residue name. So like alanine in this case. Chain identifier. So this is typically the PDB uses, the database uses chains to differentiate between different molecules in the system. Res ID, XYZ coordinates, a couple of columns that you may have already started using, occupancy and beta. These have meaning in terms of crystallography. When we use it in VMD, we typically just overload them with whatever information we want to put there. So like if you want to run a simulation with restrained atoms, you may modify one of these columns and tell NAMD, hey, look in the occupancy column for which atoms are restrained, for example. And you'll use VMD to set that. And then the last column here in the PDB, this is actually not one in the PDBs that come from the protein data bank and from RCSB. This is called segname. Now, this is an identifier we use within VMD and NAMD actually to discriminate between molecules. One of the reasons we like that better than chain is only one character. And so it gets to be quite limiting if you have a lot of different groups of molecules in your system, or molecules or groups of molecules. And so segname can be typically up to 4 characters. And so we can then also give it a more descriptive name. So you don't have to remember, is my protein A or B, you know, or is the membrane M or L, or you would just say mem, right? MEMB, right? And then it's very clearly the membrane. Okay. You don't want to rely on PDBs having bonding information, like which atom is bonded to which, but the format can have that. And sometimes you will see that, and some tools will write out that bond information at the end after the atom records. So then the question is, why, maybe I put that to you, when you load a PDB from the protein data bank in VMD, it draws the bonds, right? So how does it do that? Anybody know? Well, one of the participants.
Even without the connectivity.
Right.
I think it's basing it like if atoms are a certain distance from each other, like consider them bonded, and if they're far enough apart, they're not bonded.
Exactly. So you get a PDB from RCSB, and it only, and in, like I said, in many or most or even all cases, I don't remember, it will not have any bond information, just atoms. But VMD uses a distance heuristic to decide whether a bond is present or not. This works 99% of the time, but not 100% of the time. Okay, it's just something to be aware of. Sometimes if atoms are a little too far apart, VMD will not guess a bond. Or if you have a modeled structure and you put it in, then VMD may not be able to recognize where all the bonds are. It's just something to be aware of. That's one reason we don't want to rely on PDBs alone. One other thing to note, if you go to RCSB, you may not see PDB anymore, or it's considered a legacy format. They use this new format called PDBX/MMCIF. There are some similarities in that it will have, like, at some point it will have Atom records that look kind of similar to this. Just be aware of that and note that VMD can read these files, so it's fine. Okay. But this format I'm showing here is specific to the original PDB format. Okay. So that's what we need to start. But then, like I said, there's no bond, typically no bond information, or it's not necessarily reliable when it's guessed. So that's why we use something called PSF files, or protein structure file. So this also has all the atoms in your simulation, or in your simulation system. So in that sense, it will duplicate some of the information from the PDB, like the atom name, the res name, the res ID, but it will have also additional information like the atom type. Okay, that's important for the purposes of the simulation. That tells NAMD which parameters to use. So the parameters are based on atom type rather than atom name. That way, that keeps the files a little bit more manageable, as we'll see in a moment. It also has atomic masses, okay, right? You think, what are we doing in a simulation? We're really just doing Newtonian mechanics, F equals ma. Well, okay, you have to have m to do F equals ma. So that's stored in the PSF file. And then I mentioned these charges, in particular these partial charges on the different atoms, that's also stored in the PSF file. Okay. So what's not there? What's not duplicated? There are no coordinates. There are oh yeah, question, Ronan.
Classes are also provided in the parameter files, right?
In the topology file. So the topology file, as we'll see in a moment, is used to build the PSF file. So it reads the masses from there and puts them in the PSF file. Yeah. Sometimes they're duplicated in the parameter file, but if they are, NAMD ignores those. Velocities are never in any of these files. You can ask NAMD to write out a velocity trajectory, but that's you typically don't. You will only need that in very special cases. You'll know if you need that. And then it does not have the parameters themselves in the PSF file. That comes in the parameter file. So this is what this file looks like. It's also a fixed width file, although that I think is actually less important. I know at least NAMD doesn't care. VMD may care more about that. You see it has an index, it has a seg name that's coming up early in this, res ID, res name, so those are duplicated from the PDB file. Type, atom type, I mentioned that, I'll show you in a moment what that's for, the partial charge, the mass, and then, gosh, don't ask me what that last column's for, I don't think it does anything anymore. But anyway, it's there. Just again, to note, this is not the only form this can take. There's also something called an extended PSF file that essentially just changes the width between the columns. So the amount of spacing in order to allow for longer records. So in particular, long atom types. So instead of just 4 letters, you can use up to 6 and even up to 6 characters for the names. And fortunately, you don't have to actually worry about this. NAMD and VMD will take care of these automatically. So if you have long atom names, VMD will know, okay, I should write an extended PSF file. Okay. Topology file. Okay, now we're getting into the thick of things here. Okay, so topology file, this is the file we use to build the PSF in VMD, or more precisely in PSF Gen. So you may have already, if you dared, you may have opened one of these files and seen what this looks like. So this is the entry for the simple amino acid alanine. Okay. So you see res name, so ALA, okay, I know this is alanine. The total charge, okay, alanines are neutral. If you had something like glutamate, it might be minus 1.0 there instead. That's the overall charge. And then, there it is. And then we go down to the individual atoms. So that's the name, and then that's the atom type. So the reason we use atom types is to not duplicate unnecessarily information. So for example, you have a methyl group here, a CH3. These three hydrogens, we want to give them different names because they're distinct atoms, but they all behave the same way chemically. And in that case, we assign them the same atom type. So when going to look up parameters, so let's say you have the bond, right? The bond between this carbon and this hydrogen. You don't have to look up a different bond parameter for Cb with Hb1, Cb with Hb2, Cb with Hb3. You just look up what is the parameter for CT3 with HT3 type. Okay, and then you get the same parameter for all three of these. Okay, so that's why we use atom types here. You'll see these group entries here. So they, you don't really have to have them, but the idea behind it is that the groups are individually integer charges, so often neutral. Like if you add up here, these 4 atoms, their partial charges, you'll get 0. So again, you don't really have to worry about it, but there's some logic to it that, okay, something about, how they interact long range, then it makes it kind of smoother. Again, that's not such a critical point. One thing I should have noted, these exclamation marks, that means a comment in topology and parameter files. Okay, so everything after an exclamation mark is ignored, at least by NAMD and VMD. That's just for you. So that's why you get these nice like ASCII images here of what an alanine looks like after the exclamation marks. It's just a comment for you. Bonds are explicitly listed in the topology file. So remember, I said they're typically, or you can't rely on them being in the PDB file. But when we go to build the PSF file, we have to know for sure what atoms are bonded to what. So then we don't want to rely on VMD's guessing. We want something that says, okay, in an alanine, these atoms are always bonded. Okay, and then that gets stored, that gets read from the topology file and stored in the PSF file. So angles and dihedrals are not listed here. Does anybody know why that is? I list bonds explicitly, but I don't list angles or dihedrals. It's a little more esoteric point. Yeah.
They can change throughout the simulation?
No, they're the same. Well, the numbers change, of course, but which atoms form an angle and a dihedral. So it's always, I should be clear, the angles and dihedrals are always between bonded atoms, right? So 3 atoms in a line get an angle. Anybody? Yeah, it's a bit of an esoteric point. It's because for every possible angle and dihedral in the system, they get assigned an angle and dihedral term in your PSF file. So it's just assumed that you're gonna need them for every 3 atoms, you're gonna need an angle term. For every 4 atoms, you're gonna need a dihedral term that are bonded to each other. So there is something called impropers. We'll look at those in a little bit. There's something called CMAP. Again, now we're really getting into the weeds. CMAP is this cross-term map. It's basically corrections from quantum chemical calculations for dihedral terms. You don't, I mean, you should know what they are, but you typically don't have to worry about them. They're just handled automatically. There are things like donor and acceptor. This is actually legacy. This is from like 30, 40 years ago. Different versions of the force field explicitly listed hydrogen bond donor and acceptor atoms. And then you get these IC lines. These are internal coordinates. Again, not something you typically have to worry about, but PSFGen can use these to build your residue of interest if there are missing atoms. Okay, hydrogens are typically missing. Those can just be guessed with pretty good accuracy, so they don't even need it. But if you have missing heavy atoms, these IC lines are helpful. Yeah.
Can I look at the really show this kind of question?
Yeah. Right.
And that slide. Can you go back and see?
Oh, the PSF or what? Oh, sorry. Yeah, I see what you mean. Yeah, here.
So where is the KI. Or variable.
Where's the cat? That's the next slide. Yeah. Yeah, you had a question?
You manually add a residue to the opportunity file. Can you skip the IC or absolutely required?
No, typically, yeah, you can get away with skipping the, if you're adding one, a new residue, you can skip the ICs. As long as you're not missing too many atoms, PSFGen will handle it fine.
The legacy can also.
Yeah, you don't need this donor acceptor stuff, yeah. You don't even need groups, like I said, those are, yeah. Atoms, types, names, types, charges, those are what you, and bonds, that's what you really need. Okay, last file, the parameter file. So this is where exactly those force constants you were asking about, that's where they're stored. So the topology file is read by PSFGen to make the PSF file. And then you don't need the topology file anymore. All the relevant information got taken and put into the PSF. Then when you go to run the simulation, you give NAMD a PDB file and a PSF file and a parameter file. Okay, so the PSF file says, you know, these two atoms are bonded, they have these atom types, and then you go to the, and then NAMD is given the parameter file to say, okay, what is the force constant for that bonded interaction? Okay, and so I'm just showing bonds here, although there are also, you know, angles, dihedrals, impropers, Leonard-Jones, those are all in the PSF file, or sorry, the parameter file. So now we know the exclamation mark means comment. So you have some comments there at the start. It's telling you the functional form of the potential in this case, in the charm force field. One annoying thing, I'm trained as a physicist, so I think, okay, you know, harmonic potential, 1/2 kx delta x squared. They don't use a 1/2 here, okay, right? It's just k bond distance minus the equilibrium distance squared, okay. Okay, you don't have to really worry about that. It's all embedded within the force field, but just kind of a funny distinction. Okay, again, comments, this tells us the units. So like our force constant is kcal per mole, that's an energy per angstrom squared. That makes it a force constant. Okay, the bond, the equilibrium bond distance is measured in angstroms. This is important distinction because if you decide you want to try something for some reason, I don't know why, you want to try Gromax, for example, in theirs, they often use nanometers for their bonds. So that's, you know, subtle distinctions you need to be aware of. Better to just stay with charm and NAMD, you'll be safer. Okay, so and then you look at one of the bond records in the file, in the parameter file, you see there's type 1, type 2. So those are your two atom types bonded together, the force constant and the equilibrium bond length. And then so on and so on and so on. Important thing to note, there are going to be some of these topology and parameter files distributed with the tutorials. When you go to do your own production simulations, always go look for the latest files. It's not a guarantee that we keep the tutorials, you know, up to date with the latest and greatest. Right? So for example, maybe a tutorial uses Charm 27, which is a previous iteration of the force field, whereas now we want to use Charm 36, or even newer than that, Charm 36M for proteins. Okay, so you can get, for Charm force field, you can get the files there from Alex McCarroll's website. Okay, so far so good. Okay, so that's kind of brief introduction to the basic files we're using and how this information of the force field is stored in the topology, which then goes to the PSF, and then in the parameter file. Okay, so now I want to talk about what do we do when we don't have parameters for a molecule of interest. Well, actually, first thing to note, one of the nice things is the principle behind the parameterization is that they should be transferable. So that's why we don't have to reparameterize for every protein we're looking at. If you have one alanine, it's the same alanine in every protein that you're ever going to simulate. Okay, that's the principle of transferability. But then we have a lot of molecules, as I was saying, that may be of interest that do not have parameters. So maybe a drug or a modified amino acid or modified amino acid or drugs there. Cofactors of our proteins. Maybe you have some coordinated metal center. And typically, unless it's a very common molecule, there will not be parameters in the existing force fields for those. Okay, and then we have to develop that. Okay. There are other, so I just note here an example that we ran into. There are sometimes cases just where the form of the force field is just not quite good enough to capture some interesting behavior. That's because, right, we're doing this all classically, but we know underlying it all is quantum mechanics. Okay. So this is a case we looked at of a drug, modified form of a drug called erythromycin interacting with a bacterial ribosome. And there's a couple of ways. So in particular, the interaction between these rings here, this adenine and this part of the molecule. So they can do what's called base stacking. You may be aware, you may be familiar with this. And typically we think about parallel base stacking. That kind of makes sense, where you get some nice electrostatic interactions. And we look here, so just compare red to red or black to black. These are the energies of the interactions. Not too bad. I mean, I'm seeing maybe, half a kcal per mole difference maybe. But then there's another type of interaction these can form called T-shaped stacking. Okay, there the force field doesn't do as well. So you can see we're off by probably about 2 kcals in some cases. Okay, so these are just things to be aware of, and where there could be a need, like for this molecule, to come up with improved parameters. Yeah.
Do you really think that you can get the best method to the fact that so we know that this method are noticing that for solutions. So I'm not sure I think I understand the acronyms, but
Yeah, right. B-lip should be DFT, yeah.
you have like a correction for this person, because then you like.
I think that's the D3 is the dispersion correction. Yeah, thank you. Yeah. And I think it's a pretty big basis set too. So, yeah. Yes.
What about like post-translation modification, like phosphorylation, acetylation, and also including the metal?
Right.
Parameter.
In some of those, for common ones, you will often find existing parameters. So like a phosphorylated tyrosine, there should be somewhere in the charm force field parameters for that. If it's an unusual one, maybe not, in which case you would have to do it yourself. Or you'd have to make the parameters yourself.
And metal.
Some, like a heme is very common molecule, so there will be parameters for hemes. For like a coordinated zinc, there will be parameters for deprotonated cysteines. But again, if it's something more exotic, then maybe not. Yeah.
Are the parameters for the standard amino acids, nucleic acids based on QM calculations?
Yes, so typically, we'll see. Yeah, we'll see in a moment. Yeah. So yeah, we rely on QM for those. Okay. So, when you have something you need to do de novo, you can use, as I alluded to at the beginning, a tool that we developed in VMD called Force Field Toolkit, or ffTK. Okay. So the source paper you can see there is now over 10 years old, but we have kept it updated with new features as I'll show you. Okay. So here's the workflow. So when we think about wanting to create new parameters, we can break it down into a series of tasks. First, preparing the system, and then determining the partial charges, then the bonded terms are force constants, for example, for bonds and angles, and then the force constants for dihedrals and or torsions. And then when you've gone through all of this, then you get out a parameter file you can put into your simulation for your new molecule. Let's break this down a little more finely, though. So first of all, we need to even know what parameters we're missing. And then we're going to go through a series of steps like optimizing the geometry using quantum mechanics. So some different program, like Gaussian, for example. Calculating water interaction energies, optimizing the charges. Those are for your partial charges. For the bonds and angles, doing a so-called Hessian calculation. And then for the dihedrals, doing torsion scans. So you can see how it's broken up into steps done with quantum mechanics using a different program, and then fitting and or optimization using ffTK. So, and those are the different actions associated to each of these tasks. So ffTK, so we see the kind of the workflow here in those colored boxes. Those translate into different tabs within the ffTK plugin. Okay, so you can see how it goes step by step, building the initial parameters or finding the missing ones, optimizing geometry, water interactions, et cetera, stepping you through from left to right. So let's look at this interface in a little more detail. Okay. Right, so there are different tabs, and there are these little arrows here. Sorry, if I just go back a moment, you see you click one of those little arrows and it opens up the tab for different inputs. Okay, so like you need to put in some files. Okay, so you can hit browse, locate the file. You have some in progress parameter file, etc. There's a lot of options here, but in many cases, maybe defaults will work for you, or even there'll be ways to let it guess for you, so you don't have to necessarily know a priori. Okay, so what is ffTK providing? Its core functions are to help you set up the quantum mechanical calculations that you're going to run in a different program and analyze the output from that. So you're still having to use other tools, but it basically makes it almost as transparent as possible for you. You just set it up, you go and run it, whatever it spits out, a log file or something, you bring that back to ffTK and it will read it for you and tell you, get you or extract the pertinent information. And then it will also help you with optimization and then assessing the performance. I'm not going to go through an exhaustive list of other functions it provides. Okay. So let's just look at one example. So let's look at water interaction. Okay. So this is something in the charm force field in particular. The way that they conceive of it is that the partial charges should be optimized in such a way as to get the right energies for water interacting with your molecule. And they basically say you get that right, you get water with the molecule correct, you're going to get everything else correct as well. That's the logic behind it. So let's take this simple small molecule called pyrrolidine. So first, for this, you would have already done some quantum mechanical geometry optimization. So then you load the optimized geometry optimized coordinates. And then ffTK will automatically detect the water interaction sites. So like all these hydrogens, it'll say, okay, those in principle, could be hydrogen bond donors. And then, oh, there's a nitrogen there. Maybe that can be a hydrogen bond acceptor. And so typically, yeah, so that's here. Typically, you can trust ffTK to guess these correctly, but always take a look, right? It will show you visually, and if for some reason you think it's wrong, you can override it. So then I want to be clear, these are all individual calculations, one water at a time. We're just showing them all for visual purposes. But what it will do, ffTK will set up a number of different quantum mechanical calculations of one water interacting with each site potential hydrogen bond donor or acceptor on your molecule. And then you'll take that to your QM program of choice, run it, it will optimize the distance and angle. So it looks something like this. And then ffTK will bring that back and use that information, the optimal distance and position or optimal position of the water in order to determine partial charges for your molecule, trying to match the simulation, the MD result to the quantum mechanical result. Yeah.
And the program connects with the
It does not connect directly, so it will produce the input files. Then you have to take those files, go to wherever you're running on your desktop, on the supercomputer, run the code, and then bring the output back. A lot of questions. Yeah, maybe.
So I just want to clarify, there are two steps that you'll be going to the QM software. The first, geometry optimization.
There's multiple. There's
And then the water step.
and then bonds and angles, and then dihedrals as well.
That you're going.
So you're
to
gonna go-
Gaussian? Okay.
Yes, you're going to go back and forth multiple times. Yeah. That makes sense. Yeah.
Is there a facility to interface with different kinds of QM?
Yeah, so I'll just go ahead and tell you,
Yeah.
right now it supports Gaussian, Orca, and we just like this week, the paper just came out, we added support for Psi4. Okay, and I'll show that too. in a minute. Other questions? Yeah.
The water optimization is done one by one.
Yes, one by one. So this is just for visual simplicity, showing them all together.
So for example, how many times is the beginning to the end of the process takes?
How long does it take? I mean, it depends, right? Because you're going back and forth. You know, if you have a local installation of Psi4, say, you could do it in maybe half a day. You know, depending on how long the calculations take.
Can the water be placed with something else,
Like,
or does it have to be water?
oof, at least for charmed force field, it has to be water. In particular, it's tip 3P water. It's very specific. That's how they design the force field. I don't know. You could probably hack ffTK to do other molecules, but that's like more advanced. Other questions? Okay. Okay. All right, so you get the information back from these multiple QM calculations you've run, and then essentially what ffTK is trying to do is optimize this so-called objective function. So this is how we define it. ffTK is trying to match the energies, the interaction energy that comes from QM with what we calculate in MM is molecular mechanics. It's also trying to match the distance between the water molecule and your molecule and your molecule. And then this one looks a little stranger. This is actually the dipole moment. Turns out that may be, you want to try to get that right, because that may be more important for long range interactions of your molecule with other ones. So it iteratively tries to optimize this. And then eventually reaches some convergence criteria and then says, okay, here are your parameters, but not just that. It's not just a black box, but it allows you to look into what it's doing. So here's an example of a successive optimization procedure. So the green, so 0, 0 is what we're going for. This is the difference between MM and QM, difference between MM and QM. So 0, 0 means we're right on the QM numbers. And so green is where it starts, and you can see how it progressively gets closer and closer until eventually reaching in blue the final optimized charges, and then seeing that it matches very well with the literature. And so, and not just at the 0, 0 point, but at different distances too. It also matches very well. So that's produced by ffTK. This is just another way of looking at the progression of the optimization using simulated annealing. So starting purple is like, red is like the beginning, and then purple is like the end, and you see how it's progressively getting closer and closer to this 0, 0 here. Just different ways of optimizing. So ffTK has two two main ways of optimizing. One called the simplex method, which is like a simple search, and then one called simulated annealing, which allows it to explore a little more. So sometimes we'll use them, maybe even both. You might start with one and then use the other for a second round of optimization. So again, this is like the full-blown objective function. So looking at it in a little more detail. So again, energies, distances, dipole moment. It's what we're trying to optimize. And you can see they're different weights. You can actually control the weights. If you think for whatever reason, you think, I don't care about the dipole moment, you can weight it less. Okay. But importantly, in almost any optimization problem, you're never going to be able to fit everything perfectly. Okay. So it's not, sometimes we say, okay, we think the energies are most important. Maybe we'll weight those a little higher, and we'll weight the distances or the dipole a little less. Okay, so these are all options available to you in ffTK. So you can plot the progression. So this is the objective function there on the y-axis versus iteration of our optimization on the x-axis. And so you can see how it's converging to a relatively low number, although not to 0. And you can actually even look at the different contributions. So like maybe if it's not converging, maybe you look at these and you say, okay, the distance is for some reason it's not working well. And then you can use ffTK to maybe look, oh, not just distance, but this particular interaction for whatever reason doesn't work. Sometimes a water molecule flies away in the QM. Right? And that tells you, okay, maybe it's not meant to interact with this site, so I can just give it a weight of 0 in the optimization. Okay. So all of these parameters or whatever are available to you to optimize your optimization, so to speak. Just more plotting. What's kind of nice, if you want to include this in a manuscript, you can output the data and make a very nice publication quality figure. So here's an example of trying to test our determined parameters from ffTK. So bunch of small molecules. I'm not a chemist. Don't ask me what these are called. Just showing them here. But we used ffTK to get the force field parameters for all of them. And then we measured things like the density, the heat of vapor or enthalpy of vaporization, the solvation free energy. Okay. And you can see almost without fail, all of these numbers. So in particular, the rightmost column is the error. All of them are quite good. So like, for example, we typically think the free energy is really good if it's off by less than half a K count. That's most of them. Oh, I should have made this one red, I guess. Sorry. Only in a few cases is it getting up towards a K count. And we'd even say that's acceptable, even if maybe not ideal. Yeah.
Does this accuracy vary depending on the basis that you use in the QM calculations?
That's a great question. So that's something I've glossed over, the basis set we use. So when you do a QM calculation, there's a lot of choices one makes as well. There's the method, and there's also the basis set. So the size of the basis set. So for the charm force field, they constrain it very tightly typically. So you use MP2 method for geometry optimization, and for water interactions, you use Hartree-Fock. And you always use 631G star basis set. So if you do any quantum mechanical calculations, you might know that doesn't sound like a very impressive calculation, right? Not at all. But for historical reasons, that's what they stick with, because the whole force field is kind of built on this 40 years of methodology. And so if you try to change it, you may break something else. Although I'll show you in a bit how we change it sometimes. But typically, yeah, you just use those. Yeah. Okay. Now I said charges we get by water interactions. Just to pay homage to other approaches, like the amber force field, they have a different approach. They try to fit the electrostatic potential around the molecule, or ESP. Okay, so it's a different philosophy, but you know, basically the same end result, that you get some partial charges for your atoms. Okay, so ffTK actually can also support this, and if you go, yeah, there will be a charge optimization method drop-down menu, and you can select this rest fitting if you want to use that for some reason. Just note that, like, particularly with buried atoms, this can have a problem, because if they're like in the center of the molecule, they may not affect the electrostatic potential around the surface of the molecule. But there, you may have good reasons for wanting to use them. Bonds and angles. I don't want to go too much into the details, but essentially we create what ffTK does is it creates distortions in the molecule, small distortions, and then tries to, in and then tries to fit the energy of that distortion to a QM calculation. Now, again, getting into the weeds for a moment, in the QM, we don't actually do the distortion. Instead, we calculate something called the Hessian, which is a matrix of second derivatives in the internal coordinate space. Long story short, it gives you a number that you can then, an energy that you can then compare to this. Okay, and ffTK makes that comparison in order to optimize those bonded parameters. Okay, so bonds and angles, remember, those are harmonic terms in our force field. So we typically fit those together and then handle dihedrals separately, because dihedrals can have periodicity. So, right, it can like rotate all the way around a bond. Okay, so that's handled separately. You see, you have in the potential function, you have the force constant, you have the periodicity or multiplicity, we call it sometimes. Typically that n, that's an integer, typically 1 to 6 at most. And then you have this phase or offset angle delta there, and that is always set to either 0 or 180. I don't think I've ever seen a case where somebody goes off from 0 or 180 for that phase. Okay. Yeah, question. Sorry.
How do the routines handle systems where there's hindered rotation in
like in a ring or something?
Yeah.
It'll just blow up the energy. So there's okay, it's not shown here, but you can set, I may have it on another slide coming up, but you can set the scan range, so you don't have to go all the way around. Like, but if you do, essentially your QM calculation might crash, and you just won't get data from those really, really torqued angles. Yeah. Okay. So you do the QM calculation, do a scan about the dihedral angle, you get the data back, and then we make plots that look something like this. So this is, importantly, this is not angle, although it's close to angle, it's conformation on the x-axis, yeah. ffTK for modified bases for nucleic acids. I don't know that we ever have, but you could. I mean, I think it'd be pretty straightforward. Standard procedures. Okay. So for the dihedrals, so the QM potential energy surface, so it's energy on y-axis, conformation on x, is in black. From QM, our initial from the without any dihedral parameters yet is in red. So you see the red and the black, or let me use my pointer here, and the red and the black, pretty different. And then the first attempt is in blue. Okay, you can see it getting closer, but it's definitely not there yet. But then we do multiple rounds of, in this case, simulated annealing. So in this case, it took 7 rounds, but after 7 rounds, the fit is really good between the and QM. The reason you need to do multiple rounds, optimization is a really tough problem. And particularly when you're in this high dimensional space of many parameters, right? It's not possible to search the whole space exhaustively. So these methods are trying to kind of jump around and find a region of the parameter space that's reasonable. And then from there, focus in on getting the details worked out. So that's why we often have to do it multiple times, multiple rounds of optimization. Okay. So with regards to the dihedrals, there's a lot of subtleties. Well, you know, you could say that about everything in the force field, but especially the dihedrals, because we have, let me just jump back to the potential function for a moment. It's a sum. So even for one set of 4 atom types, you could have multiple terms in your dihedral function, potential energy function, because you can have different ends, 1 through 6. You could have different phases. So we have to make decisions about this. ffTK is not going to be able to tell you what to do here necessarily. So you could just have, you could say, okay, I'm going to have n equals 1, 2, 3, 4, 5, 6. I'm going to include all of them. Why not, right? Give it as many parameters as possible. Well, okay, you know, that could work. Maybe not. Or you could think a little more carefully and try to pick only a subset of these, like 1 multiplicity, 1 or 2 multiplicities, 1 phase, locked phase. Okay. And inevitably, regardless, you're making some trade-off here. So let me show you what happens. So in this case, for this is antibiotic to erythromycin, and in particular, we're focusing on the imidazole pyridine moiety. And so the first attempt was, let's just include 3 different multiplicities, n equals 1, n equals 2, and n equals 3, right? The more, the better. And sure enough, you fit them. Hey, that looks, you know, I'm plotting, you know, red is the MM, black is the QM. That looks like a really good fit, right? You know, it's not perfect, but pretty good. Okay. But then what happens is you go to simulate it with those parameters, and you get bending of the rings, distortions. And we know from chemistry that those rings should be planar. There's a lot of double bonds in there. So what went wrong? You know, we made these great parameters. It looks like it fit, and yet nonetheless, it doesn't seem to work when we simulate it. Well, we didn't think carefully enough about the chemistry. So dihedrals in these planar rings will typically only have a multiplicity of 2. So rather than including n equals 1, n equals 2, n equals 3, we only include the n equals 2 term in the dihedral fitting. And in fact, the fit is even better than when we had 3 terms. You might think that should be impossible, right? If I have more terms, how can it be worse? Well, again, it's because the optimization problem is not an easy one, right? And there's no guarantees that your algorithm is going to find the global optimum, right? Sometimes you have to help it along. Okay. So again, our molecule now with just 1 dihedral with n equals 2, and it maintains its planarity, just as we want.
So
Yeah.
this one, in spite of your improper dihedral constraints, it is still buckling? I mean, those rings?
I think, no, that was without impropers. You're right, you're right. So we could use impropers to just paper over that. But ideally, yeah, we want the right dihedrals rather than having them fight each other. Yeah. Now you can actually still have other issues like this eclipsed conformation of this of these groups there. And so you can take care of this by restraining the phase of those dihedrals to 0. Okay. Again, just basically saying that math and optimization algorithms are no replacement for knowledge of the chemistry of your molecule. So, but I'm not a chemist. What do? Right? I'm a lowly physicist. I don't know these things. I don't even know what to call them. Well, there are some guides out there, and I linked to one here. This is from a guy, Keno, who used to be in Alex McCarroll's group, and he still maintains on his website a really nice guide to how you make these decisions about which dihedrals to include or not include. So definitely, if we have a new molecule, at least for me, I might refer back to this to know whether I should include like n equals 2 or 1 or 3 or whatever. Okay, so we've made a couple allusions to already to improper terms, as was just mentioned. So I did not include this in the original potential function I showed you because they're not always used. So impropers are used in very specific cases where sparingly, where you know that a certain group of 4 atoms should be planar. In particular, it's 4 atoms with 1 central atom, so 3 of them bonded to 1 in the middle. So if you know those should be planar, you can add an improper term to your force field, and you notice this is a dihedral angle, but instead of that cosine, it is harmonic. And so this basically means it does not have periodicity. It's trying to keep it close to probably 0, or at least some limited value. ffTK can also fit these for you, but you have to tell it which ones you want, right? Because I said they're used sparingly. So you have to know the chemistry of your molecule, like in a ring with a lot of double bonds. Then you'd say, okay, I know this ring should be planar. So then you can, in addition to being careful with your dihedral selection, you can also fit some improper terms in order to ensure planarity is maintained. How am I doing on time? Okay, it's only 10. Okay, we have time. Okay, any questions so far? Any burning questions before I continue? Good. Yeah.
So there is an order in terms of these optimization.
Right.
So, for example, if you optimize charges first, the bonds can go somewhere else. If you optimize bonds first, that will influence your charges. So is there some implication?
So that's a great question. So actually, yes, if you want to do this self-consistently, you actually should probably go through the procedure at least twice to ensure you've converged. Right, because the bonds and the dihedrals can come back and influence the partial charges. We typically don't do that. It's typically not necessary, but it's definitely something you can do if you want to be absolutely sure your parameters are good, is to go through the procedure twice to confirm that you've converged. We typically find one pass though, they're good, and the second pass really doesn't change much. Yeah. Yeah.
To clarify, so then is the geometry optimization, does it consider partial charges? With
No, right, what does it do? No, the QM, right, in the QM, right, you have, there's no such thing as partial charges in the QM, right, because you have the electrons. Yeah.
So then what part are you?
MM has partial charges, QM has, there's a total charge, there's no partial.
So,
There's only one
right,
charge.
right, so this you're not doing, there's no MM component to this.
So what point are you talking about this being?
Oh, I mean, the
Cyclical.
order, right? I mean, so if, for example, if you optimize bond parameters, okay, in the charges you are determining later. But if you optimize charges first, but then the bond parameters could be different.
Right.
So it's those.
Well, actually, let me temper that a bit.
Yeah.
When we do the charge optimization, we use the fixed geometry, so the bonds will not influence that. But it is true, at least for the bonds and angles and torsions, there could be influence, right? But the charge optimization is using the QM optimized geometry, so that part will not change. Yeah. Yes. Okay.
Yes, assuming that I have a commodity cluster, difficult to converge. And I want to do like ab initio optimization of the product for a new molecule. Like this new drug is very exotic, organic groups. I don't want to go through Alex's online. I want to do everything with ab initio from the beginning. Can you give us some perspective how much it's gonna take me in terms of human time and computer time? How many hours?
Right, it's not gonna-
It's not gonna be a big one.
No.
Drug, so it can be anywhere.
20.
20 atoms.
not
30.
much. You could run that on your desktop, depending on what software you want to use. But like if you're using Sci4, you could run that on your desktop. I don't know off the top of my head how long it would take, but we're probably talking hours in the worst case.
But we're talking about like the charge optimization.
I mean, the charge optimization, those are really fast because all you're doing is it's changing the distance and doing single point energy calculations. The dihedral scans are slower because you're doing it's relaxed optimization. So then it's going through this self-consistent
Take the value of the angle, then you relax.
exactly. So those are slow in the queue, slower. The Hessian is very fast.
Very fast.
Yes. Yeah, Ahmad.
Could you discuss the charges for your optimization?
Do we?
That there is
I
no
think-
partial charges in QM, but they do have some partial charges based on some.
So this, this is where these are decisions made over 10 years ago. Yeah, ffTK will take something from the QM to initialize the optimization. I can't remember if it's Mulliken charges or something else. Yeah, but it will take some, there is something from the QM, but it turns out that's usually a bad starting point. Or it's just a starting point. It's not an ending point. Yeah.
I think Tom uses Mulliken.
As a starting point. Yeah. Okay. Right. So like, in the case of dihedrals, wait. Yeah, so here, that's one reason we fit these all together because we want to know how they relate to one another. So you could fit them one by one. And actually, sometimes we do that, but even if we do that, we always go back and then do one last fit globally so that the global minimum is there. Yeah.
So there are, for example, there are multiple dihedrals. I mean, in a given molecule,
Right.
there are many rotatable bonds.
Right.
And some of them have common atoms, right?
Mhm.
So, I mean, there are separate optimizations for each dihedral with, each phase and, multiplicity. But then there are other global optimization
So
across all the dihedrals.
right. So the standard way is you just do them all at once. That's why we have hundreds of configurations, because this may be the first dihedral, and these may be the second dihedral and the third. So they're all fit together. I just say sometimes to help the optimization along, we might do them one at a time, but then we always, just to get starting points, and then we go back and do it globally again. Yeah. Okay. So let me skip through these. Okay. So I'll move on. I still have a bit more I want to discuss here. So what about polarization? So you may have heard something about polarizable force fields, and there are some options out there. And basically the idea is, so in our model, when we come up with these partial charges, which now we see we get from the interactions with water molecules, those become fixed for all of time. In your topology file, the charge on the alpha carbon of the alanine is the same in every alanine and every protein in every simulation. But we know in reality, like if an ion comes close to our molecule, it might change the charge distribution within it, right? In other words, it can polarize. Okay, the electrons move around. Okay. So there are different ways of incorporating this into our simulation. So one way is something called like induced dipoles. So you see a little dipole arrow on that atom responding to the ion. Another way is something called a Drude oscillator. So you put a little particle on that atom with a little bit of charge, and then that little particle can move in response to the ion coming close to it, thereby, again, changing the polarization there. And then there's also a method called fluctuating charges, where instead of so you don't have any additional particles, but the charges themselves, the partial charges can change. So these are all valid approaches, and different force fields may use different ones. So since we're talking about the charm paradigm, mostly I'll point out that in charm, the developers, particularly Alex McCarroll, they prefer the Drude model, in which you have additional particles on your atoms with a little bit of mass and a little bit of charge that respond to the electrostatic environment around it. Okay. So this is supported, this Drude force field is supported in NAMD, but a few caveats. There's more parameters you have to figure out if it's something you don't, if it's a new molecule. The time step has to be shorter. So we're using typically 2 or even 4 femtosecond time steps with hydrogen mass-free partitioning. But when you have these Drude particles, because they're very small and they move very quickly, you have to use 1 femtosecond, or even in some cases 0.5 femtosecond. And then because you have these extra particles, those have to be tracked in the simulation. So now you have up to twice as many particles as atoms. So again, you're now between the time step and the number of particles with Drude, you're getting probably a factor of 4 slowdown in your simulation. Okay, something to be aware of. But maybe it's important, right? And we have faster computers, so right, maybe it's worth it. We want to do this. Well, let me show you an example. So this is a project we did looking at the folding of GB1 beta hairpin. So just less than 20 amino acids, folds into a nice beta hairpin. And we wanted to get the free energy of this process. And we did it as a function of a couple of different reaction coordinates. We heard a lot about this yesterday, how to do these calculations. So in particular, we looked at the number of hydrogen bonds as one coordinate, and the radius of gyration of a core set of hydrophobic residues. And so when we do our free energy calculation, this was using umbrella sampling. We see, okay, so the folded state is there on the right side. Or, sorry, I should keep using I really should use this. Is there on the right side, that's low energy. And the unfolded state is up here. So high radius of gyration, low number of hydrogen bonds. That's the unfolded hairpin. Okay. Okay, so that's the basic idea of what we did, but we did this for a few different force fields. So we used Charm 36, that's kind of our bread and butter standard force field we use, fixed charge, not polarizable. We also used another one, kind of an interesting one called Charm 22 star. This comes from D.E. Shaw Research. You may have heard of them. They have the Anton machines, or they make them. And then we use this polarizable Drude force field. Okay. So experimentally, it's expected that the folding free energy is almost 0. So what that means is it basically spends half its time unfolded, half its time folded. Okay. So it's maybe a little hard to tell from these 2D plots. So we integrated out one or the other coordinate to get the delta G in 1D plots, depending on which we integrate out. We get slightly different numbers, but it's around, for Charm 36, it's around -7. Okay. So that suggests that the folded state is severely overstabilized in Charm 36. So even these very good force fields that we use day in, day out, sometimes have issues. Charm 22 star, interestingly enough, even though it's a fixed charge force field, it's only about overstabilizing by about 1 kcal or 1.5. That's not too bad, or 2. And Drude actually understabilizes the folded state by, or overstabilizes the unfolded state by about 2 kcal. So kind of our takeaway from this study was, well, okay, Charm 36, and in particular was a salt bridge that was too strong in this, so kind of an unusual case. But the Charm 22 star and Drude, both off by a little bit in different directions. But, you know, so in the end, was Drude worth 4 times the cost for this? I would say no, probably not. Like we are not typically using Drude And so I would suggest you only use it if you have a really good reason to use these more expensive polarizable force fields. And that could be like, you know, something that strongly polarizes, like maybe in an ion channel or other case, yeah.
I mean, your conclusion is really bizarre. I mean, it's essentially like, you have to spend more. Is it like the perspective that you offer? You're gonna spend way more computational time.
Or not.
It's something shitty.
But it's not shitty, actually.
That's shitty.
Oh.
But you know, not
Yeah.
perfect. I've heard this time and time again, that it doesn't deliver the promise. The promise was that we would get a better description, better equilibrium between unfolded and folded, better description of the bits. And it's not quite delivering.
So I'll say two things about that. So one, because you have more parameters to fit, it's just harder to get them accurately, right? Because optimization is a tough problem, and so I think, you know, the Charm 36 is the culmination of 40 years of work, of hard work by many people. Druid has been around for less than 20 years, and an orders of magnitude fewer people are using it. So perhaps it just needs more time to improve. But the other, and then conversely, the fixed charge force fields have had that time to get better. And I think in that case, they're really reliable for most situations. So something like you would not expect for folding of a beta hairpin for polarization to matter much. And sure enough, that's why we see, I think, that it does not improve anything significantly. But again, if you have cases with strong polarization effects, then you're going to need it.
Or
well, and be fixed, right? Can paper over some of these issues for sure. Yeah. Yeah, I don't think we're going to get to, at least in our careers, we're going to get to a point where we just switch over and say polarizable all the time.
no, but I mean, and that's in line with section to the some developing different approach.
Yeah.
More physics-based.
Amoeba, yeah.
Amoeba and deep wonder.
Mhm.
And maybe there is also something with what we want to hear that, but I think it's physics. It's not the panacea. It's
Right.
not quite anything I'm sorry.
Sure.
It's just a trick that you said, more expensive, but still remain within the realm of point charges. And that's the selling point. Because then you can use your TNE without any modification.
Right.
If you go to this induced dipole, in fact, like multiple extension.
Right, they also have quadrupole, yeah.
Then you have to go to way more sophisticated.
And it's much slower.
And it's much slower.
Yeah. But it may be worth it for special cases, but not universally is all I'm saying. Yeah, Gary. Yeah.
So do you have any intuition of why the C22 stack worked here?
It escapes me. I think in our paper, we did look at the details of why it's better. Yeah. They basically fit on different data, and that turned out to be better for our case. Yeah.
Is this generalizable to all polarization? Or is it specific?
No, I wouldn't even say it's like polarization. It's just, again, maybe it's fortuitous, but at least for looking at beta sheets, we have decided to use Charm 22 star. Good. Okay. Okay. So I want to show another example, and this is a case of a drug binding to a virus. So first of all, what are viruses? So they're protein shells encapsulating genetic material typically. So simulations have made a lot of impact on these, starting with the smallest one, STMV, satellite tobacco mosaic virus, now almost 20 years ago, hepatitis B virus, HIV, 64 million atoms done with NAMD over a decade ago now. And even ones as big as like the whole SARS-CoV-2 variant. So that's not just the proteins, but the membrane envelope surrounding it. And that's hundreds of millions of atoms. That was also done with NAMD a few years ago. Okay. So you can do simulations of viruses, focusing on hepatitis B in particular. So again, protein shell, in this case, composed of 240 copies of the same protein called CP. And we would like to figure out how small molecules can interfere with this protein shell and then ideally break it up or prevent it from forming in the first place. So here's an example of the effects of an example of a small molecule that's already known called AT130. So this is the assembly process. So dimers of the protein go to tetramers, go to hexamers, and eventually bind all together into the capsid that has the genetic material inside. This small molecule, AT130, interferes somewhere in this process, changing the conformations of the proteins. In this case, it's actually counterintuitive. This molecule accelerates the formation of the capsid, but the reason that that's beneficial is that then the genetic material does not get inside because it assembles too quickly. Okay, so we would like to, in our group, we would like to understand exactly how that small molecule interferes with this assembly process. But to do that, we're going to need force field parameters for it. So there's kind of this molecule ended up providing an interesting case study in that it has that orange there is a halogen atom. In particular, it's a bromine. So halogens are your iodine, chlorine, bromine, or fluorine. Okay. Oh, it also has a very flexible torsion at the center. Yeah. So there's the bromine atom. And it can interact differently with different parts of the molecule. So this is kind of interesting. So with a polarizable force field, that would handle that very well. Admittedly, we did not even try that because there's a simpler way. So in the charm force field, they've added something called LP particles, so this is not a polarizable force field. This is just an extra particle added to these halogen atoms in order to capture a particular electrostatic effect called a halogen bond. Okay, so what's a halogen bond? This is kind of getting into the chemistry, but it's essentially a particular directional interaction reflecting the asymmetric distribution of the electrons around that atom, around that bromine. So in particular, this normally you would think of it as electronegative, but there's a small positive region called the sigma hole. And so that's what this little LP particle in yellow there is giving us. It's giving us that positive region, that sigma hole there. Okay. So this is just a slight tweak to the charm force field, but potentially very valuable when we're talking about drugs, which often will have halogen atoms on them. Bromine or fluorine actually does not have a sigma hole because it's so electronegative, but at least bromine or iodine or chlorine, okay, will have this. Okay. And so we now support in ffTK the parameterization of these LP particles as well. Okay. So just, we went through actually Andrew, who's Andrew here? Well, anyway, Andrew, who's around, did this, doing all the scans with ffTK and QM software, getting the energies, and then fitting them. Okay. So this one was pretty challenging, again, because it has so much flexibility that it took a lot of rounds of repeated optimization to get a good fit. Okay, so it looks something like this. So this is dihedral energy, dihedral conformation. And it's a lot of data in here. We just emphasize that ffTK fitted parameters with or without the LP. Actually, we tried both, but regardless, the ffTK parameters were necessary to get a good fit. And if you just use some like web server to get the parameters, they perform very poorly. Okay. Yeah.
The starting point of the optimization came from a crystal structure.
Yes. Yeah, I think it was a crystal structure of it. Yeah, of it bound. Right. Right. Okay. Okay. So I've been, mentioning at a couple points the different codes, quantum mechanical codes that ffTK supports. I want to emphasize this one we just added. So first of all, Gaussian, if you're an academic, you can probably get access to Gaussian one way or another. Some of the supercomputing centers have it. You can apply for time and then get access and run it for free. But if you're an industry user, you go to Gaussian and say, I'd like to run your software. They say, pay up, give us $30,000. I'm just guessing. I don't know how much it costs, but a lot. So then a few years back, some people in Urbana added support for Orca, but it turns out Orca, while being free and easy to use for academics, is still not free for industry users. So if we'd like, people in pharmaceutical companies to adopt our tools, ideally, we want to give them something that's free even for them. And so that's where we turn to actually my colleague at Georgia Tech, David Sherrill, who develops a code called Sci4, which is actually, it's very nice, very easy to use quantum chemistry code. And now we added support for that in ffTK. So it's not going to be in the version I think you downloaded just this week, but it will be in the next version that comes out. And so in this case, again, everything's transparent for you. You just have to go find Sci4 online, download it, and then ffTK will give you the input files to run it. Okay. And just showing this paper is just came out this week, actually, online. And you can see we did lots and lots of comparisons to make sure it was working as we expected. For example, the geometries there, they overlap pretty well. You almost can't see the differences. And then the energies. So these are like dihedral stands again. You compare the 3 different QM codes, and they look quite similar. I just note, actually, the one thing that gave us a lot of trouble, you almost can't see it there. Where's my point? Yeah.
There are the 3. I assume that all things equal. I mean, using the same basis set, the same level of theory.
Yes. Yeah.
Just like their implementation.
Right. So there should in principle be no differences, although there can be slight numerical differences because of, for example, different convergence criteria used internally in the code. Yeah. So in fact, those small numerical differences came up. Orca gave a small dip here. You almost can't see it compared to Gaussian and Sci4, which did not have it. That actually gave us a bit of trouble because then the sampling in the MD was a little bit different. And so we had to try to figure out where that arose from. But it is just different numerical criteria within the code. Okay. So, we've been at this for 90 minutes, so we probably need a break. Just concluding, there's a bunch of steps involved in parameterization. I can tell you, really the whole impetus behind ffTK is over 10 years ago, I said, you know what? I got this new molecule. I want to parameterize it. And that was like a months-long journey to actually figure out. And then you come to learn almost nobody at that time was doing parameterization themselves. And so it showed there was a desperate need for tools that can help with this process. And so that's why we created ffTK to bring parameterization to the masses. And so now it really can help with all of these different steps in the process. So it's not black box, but you probably don't want it to be, right? As we saw, there's still room for having some chemical knowledge, and making critical choices along the way about what to emphasize. But ffTK streamlines all of that. Yeah, Marcelo.
one last question before, just because they're still setting up the coffee break.
Sure.
Side, so.
Please ask away.
I really like using ffTK for small molecules, and then once I had to parameterize a modified heme,
Mhm.
a big extension of heme. And so, of course, the QM gets very expensive when you have something like a heavy metal or with a big ligand.
Yep.
Are there tips and tricks or, you know?
So wait till after the break and we'll talk about that.
Cool.
Yeah.
Perfect. I was
That's
hoping to extend the session.
We
can take 2 more minutes.
Yeah. Sorry.
So I haven't used any other QN configuration other than can you comment on the other softwares, whether they say scale up to more CPU or they do support like that?
Oh, that's a great question, right? Are the other QM softwares better or worse computationally? I have no idea. I mean, Sci4, at least they sell it. It's very fast and efficient. So, but I have not done comparisons between them specifically. Yeah.
Yeah, because I had experience of working out an office that is around 50 atoms and doing out with that is a filter.
It's a great question. Maybe it'd be worth it to try Orca and or Sci4 and just see if it works better for your purposes. Yeah.
It's a little faster than that.
Okay.
But it has some optimization areas different, and then the version to check that, but it's good. I have been working with 100 atoms and also and what is a little faster.
Good to know. So this is my last slide before the break. So other questions? Or
Okay, so yes, sort of like a bigger, a broader question, like, you talk about the transferability principle. So how do you actually validate or verify that actually it's true? In cases?
It's the assumption, right? So that's kind of, again, underlines the term force field, that if you get the interaction with water right, you're going to get everything else right. Is that always true? Your mile is definitely, if there's strongly polarizing effects, maybe not.